Thank you for the introduction. And just for you all, my name is Anthony. I'm a technical product marketing manager at Lambda, and today is designated MC. And so just as our host here noted our agenda items, these are a few of the things that we're going to go through this hour during our workshop. And I'd like to introduce my colleague, Danny Kraus, who will be presenting to you Neural OS, our neural operating system.
I wanted to provide a little background about how I think about agentic AI, sort of in terms of this project, because it can mean a lot of different things to a lot of different people. So Nolan Bushnell had this famous quote, and I literally can't see it, so I'm going to have to paraphrase, but it's basically, everybody who's ever had a hot shower has had a good idea, but it's the people who get out of the shower, dry off, and then go do something that make an impact. And that do something part is where I think the agentic AIs can really shine, right? Like, you can have more and more complicated layers of something that takes text that a human gave it and spits out a better answer, but that doesn't do anything. That's just text coming back. So you got to wrap it in something that can do something and then hopefully get that feedback loop. And so we made this kind of crazy idea. Our CEO started working on it, and we kind of took it over. And he basically said, like, hey, like, a computer, is a series of programs. Talented people program it. Hopefully, it's bug-free, of course, never a problem. But when there is a problem, then you got to release updates, and then you got to have more people working on it again. And you're sort of like, okay, imagine a world in which the LLMs were good enough that they could be the computer itself, right? You could give it a complex enough prompt that says, like, hey, you are a computer. You're going to accept these inputs from the user, and you're going to do whatever it is that they want. And then you're going to pretend that you're a computer and keep going. And so we whipped together this demo that basically it's wrapped around just like HTML and CSS right now. So you give it a prompt. It took us a while to craft the prompt that was able to like do these sorts of things. But I originally was just going to ad-lib this with no visuals, and this morning I was sort of like, I don't know, let me get Neural OS to make a slide. So I literally asked it, like, hey, I didn't tell it the quote. I said, hey, do the Bushnell quote about the shower and generate an icon that's relevant. Unfortunately, the first time I did this, it generated a better icon and I lost it, but this is the second time that I did it. I still think it's doing pretty good. And so the idea behind it is that you can have this interaction with it, and it not only gives you the sort of visual possibility of whatever's coming back, but it can also network to other ones. That was the other thing that we wanted to do. So we have a relay server on the back end that connects them over their IDs, and so you can actually have these things talk to each other, which, sorry, again, I didn't plan on doing this exactly this way. Nope, wrong way. Okay, so here's an example of a random thing that I did this morning where I was like, hey, establish a chat with this other instance. So you are seeing one instance of it, and there's another one that I have there's an incognito here, an incognito window that's the other instance that sent the messages. So I asked it to establish like a synchronous chat application with, and you give it the ID of the other one, and then it would synchronize them and actually put them together, which I think it did a pretty good job. And I wanted to also sort of demonstrate that it can actually like go out to the web and do things. So I said, hey, tag each text thing with an image that's relevant to whatever's being talked about. Again, traffic was bad, Golden Gate Bridge with a bunch of cars, and it's like, hey, I should take my bike next time, and it's just a picture of a person with a bike in a field, which is not bad for its first try. And I can't see too well, but we've had a lot of fun doing these things. We initially had a bunch of questions about, like, what's the security model look like when you're like having an LLM interact with another LLM that's not yours? And we decided to just blow open all the gates and have no security. So you can, if you get somebody else's ID, you can have it, pop up annoying sounds. One of my coworkers did that to me. It just like opened up in my web browser without my knowledge. But the idea is that you can sort of wrap your mind around how you would have instructions to an LLM that would be able to generate these things. And then you can get into the sweet spot of people who are not necessarily super technically minded, but want to make something. And they could figure out how they want to make something. And then you get into this really interesting part of, well, it doesn't quite work right now, but if I shelve this for, honestly, a frighteningly short amount of time, until somebody comes up with a better LLM, and then I just put this exact same thing back into it, I can effectively get better outputs with the same sort of source code. That's the LLM that you first, or the prompt that you fed into the LLM. So then like the prompt basically becomes the source code. And we added some glue here. There's a bunch of things that it can do. You can actually, you can ask it what to do, what it can do. So we gave it some ability to go to the web and like get things, which has been fun, definitely. But I think that one of the things that's most interesting about this is that everybody's experience, even my own experience, is different, because there's an LLM that rendered this whole operating system each time. So when I log in, like sometimes there'll be icons on the left, sometimes there won't be, sometimes they'll be in color, sometimes there won't be, and different neural OSs, when they get these messages across the network, then that is run through inference again, right? And so sometimes this synchronization between things works, sometimes it doesn't. I like lucked out that the first time that I did this for this demo, it worked. I thought I was gonna have to capture some screenshots for it, but we're really hopeful that you could play around with it and figure out if there's something there. And we're gonna work on extending the things that it can do and giving it more agency and putting my computer to sleep. And yeah, that's basically how NeuralOS works. You can go to neuralos.com and try it out. It's open to everybody. Yeah, that's it. Thanks so much.
And that's not all we have to show. Here in the next segment of our presentation, we'll be doing a demonstration of how you could deploy AI agents using our managed serverless inference API. So that's the presentation I will be giving right now. But before we get there, I'd like to set the stage a little bit. So let's run a hypothetical scenario, and let's all pretend for a moment that we work for an organization called Space Outfitters. And just imagine Space Outfitters to be just what it sounds like, a shop where we could outfit you with all your needs for your space travels. And so in this hypothetical example, let's just put ourselves in the role of an employee there that might be wanting to deploy AI agents to automate some of their executive reporting. So in this case, in this example that we're going to show, we have created 3 different agents, one that reports on both consumer sales, another that reports on B2B, like distribution sales. The second would be summarizing campaign impact and growth metrics for our marketing operations agent. And the third will be one for customer supports, one that summarizes issues and satisfaction insights. And then wrapping this up with a presentation to the board. So before we show you how to deploy these agents, I just want to give you like contextual understanding of the workflows if you're not already familiar with that. So what is an agent? An agent is simply an automation workflow that is prompted with a role. It's granted a title, in this case, sales reporting agent, and it comes equipped with a goal and a backstory. These are all codified in YAML files that are accessible in our GitHub repo, which we'll display here in a moment. And these agents are pretty purposeless if they're void of tasks that include descriptions, expected output, and are attributed to said agent, as can be seen here in this YAML file related to the tasks. And lastly, these agents are incomplete without their tools. So in this case, it's a Llama index CSV reader with the following code can be seen here. Now, how are we structuring these agents? So like I mentioned, the first sales ops agent is one that's summarizing reports for both consumer and commercial sales. And this singular marketing ops agent is doing the same thing and consolidating the insights for consumer and commercial sales into a singular report. But as you could see, the customer support operations agent has a little bit more of a streamlined workflow. But we just wanted to share this as like a visual representation of how this deployment kind of works under the hood. And as you can see, this is just a visual of that workflow at a more granular, data-driven level. But this state of the business report here is essentially the format for the reports that this agent will render. So it includes an executive summary, key metrics, as well as month-over-month performance comparison. So this is the anticipated output of the agents that we will be deploying today. Now, how these get deployed, like I mentioned, we have a repository available on the Lambda GitHub titled AI Agent Masterclass. Now, no need to feel the pressure of following along with this exercise. I could give you all details to kind of replicate this at home, and I'll be providing you instructions as to how you could do that along the way, and we could save questions for the end. But very simply put, it's just as easy as we'll be demonstrating for you today. So it starts with ensuring that you have all the proper requirements. So in this case, ensuring that your Python is up to date, that you've downloaded the OpenAI Python library with this command, pip install. Ensure that you have a Lambda Cloud account with an API key created. And the important step here is to ensure that Docker is actively running on your desktop. Simple enough. So in these short few steps, we'll show you how to run an agentic AI example of your own. So in this case, you would be opening your terminal, cloning the repo, and then checking out the correct branch. So you just git clone the URL for the repo, and then cd to the path where that repo is saved locally. From that point forward, you will be creating and saving an .env file that includes your Lambda API endpoint key, and you could feel free to choose your preferred model. So selfish plugin here. We recently launched an inference API about 6 months ago. We host up to 19 different open source and proprietary models. So you could swap out any of your choice here. We include Llama 4 Maverick because it is capable of some multimodal use cases. All right, and in this example, we're just showing you how to test that API. So you just enter the command source.env, and you submit a curl command to the API key, and it will generate text like so. And this just shows you the availability of the different models that we offer here. Great, and the last and final step is building your crew of agents. So this was built using Crew AI. They happen to be a partner of ours that we work closely with sometimes, but in this case, all that's required is building the Docker image, running the container, which copies the reports. So once again, just copy this command and drop it from our repo and drop it in your terminal. So what does that look like exactly? Really quick, I am going to navigate to my desktop, which is usually crowded with tabs. But here in this case, I just wanted to walk you guys through really what that looks like. And don't be alarmed, this produces a great many number of tokens. But as you could see here, I followed the examples that I walked each of you through. Here in this case, I had the repo saved already. So I just CD'd into the folder. I tested the API in this case, and then I entered the build Docker image and run container command here. And so what that does is it reviews all of these the metadata in each of those files. And as you can see, it's formatting the output in just the way that we've requested, and is analyzing each of these reports. These reports are generated using synthetic data, so no privacy concerns here. And just as an example, this green text are like the token output. So as you can see, it's given the task, And here is the synthetic data from those reports that it's analyzing. And these are the system instructions. Now the output of that can all be seen here. I just want to scroll to an example. Like I said, it produces a great many number of tokens. And as you could see, here are some of those reports. This is specifically on the B2B sales reporting. As you could see, it generates an executive report informing you that close one revenue is up by, or decreased 15% since February of 2025. So this is just high-level overview, but as you could see, pretty plain and simple. You know, given your data sources, this repo, and our inference API. So just a quick example of how you know, multi-agent workflows can be deployed in the workplace. And this is just the second segment of our presentation. I would like to introduce our colleague Amir, who will be sharing more details about our research and multimodal challenges and tools. Thank you.
Thanks for the introduction. I'm Amir Zadeh. I'm a staff scientist on multimodal learning at Lambda. We have had a lot of progress, obviously, in AI within the last 2-3 years. The main reasons, we had compute, a lot more compute, and a lot more data, right? And now we have all these like nice foundation models and all of the good things that they can do, such as agents. But the outlook for multimodal learning, where we have all these different kinds of data that can come from different sources, and some of them may not actually be in the petabyte scales that we would want them to be. Text is easy, images somewhere in the middle. Video, now we're kind of like threading on these dangerous gray areas. Do we have enough videos or not? Then we go into like MRI, CT scans, infrared, all of these modalities that we just don't have enough data, right? So there is also another piece of bad news, is that even in those areas that we do have enough data, we're going to run out of new data points by 2028. So that's the projection that we have. So we need to start thinking about, okay, compute seems to be the area that we can push further, unless we get everybody on the planet to start annotating. But that's not going to scale either, because if we double the size of this, the training will probably take another extra day or two. So this is going to be a problem, ultimately. So today, if you look at what we have in the field, primarily we have two camps of foundation models. One is camp diffusion, and one is camp autoregressive, right? And they are being studied on different areas, meaning that vision people are now trying to do autoregressive, diffusion folks are trying to do text, and so it's not quite clear which one of these camps is going to be the ultimate winner in this situation where we're going to run out of data but not out of compute. So this paper talks about, it's a collaboration between Lambda and Carnegie Mellon, where it basically says diffusion will ultimately beat autoregressive in data-constrained settings. It's just a matter of compute, and diffusion will do better. So I also want to introduce quickly the co-authors. Mihir and Mengning are both students at Carnegie Mellon. Katerina and Deepak are professors there. I also got my PhD from CMU, so. Let's talk about diffusion training. Diffusion training, you basically create these masks, and at least in the discrete diffusion, you create these masks, you try to figure out what those masks should have been, and you get rewarded for predicting them correctly, or you get penalized if you don't predict them correctly. Autoregressive is also a case where we basically try to always predict the next token within a sequence and, sort of like go from, I have 3 masks, then 2 masks, then 1 mask. So we want to do this study where there is this notion in large language models that you need to train for 1 epoch only, right? There's no need for extra epochs. And part of the reason why diffusion folks have fallen behind is that we stuck to that belief that 1 epoch is always going to be the same, right? That's true for a case of autoregressive, meaning that let's say if I have 100 million tokens, right? At some level of compute, the tokens are no longer making any difference. My loss is not going down. And the flops that I throw out at this, even if I go in the scale of exponents, is not going to help me as much. But on those same 100 million tokens, if I just let diffusion train for more epochs, and this is on more epochs set up as well. So both of these are being fairly compared together. Diffusion will ultimately beat autoregressive. What's even more interesting is that there's this moment of critical compute point, meaning that there is a critical compute point where we can also identify exactly where that point is with certain approximations. If you tell us, for example, what number of tokens you have and how much flops you have, you'll be able to predict this critical compute point, and if your budget allows to go beyond this critical compute point, you can throw more GPUs into the pipeline and get better. We also do this for 50 million, and another interesting trend shows up is that diffusion is also more data efficient, meaning that ultimately autoregressive is incredibly data hungry, but diffusion can use lower amount of data in order to do better. So there is a way to compensate for the flops issue that we had earlier. So the check of these Pareto optimal and critical compute points is interesting. We want to sort of like get a little bit deeper into this. There's really one thing we need to be concerned about. There are some ways in machine learning to calculate scaling laws. In the paper, we introduce an extension of those that applies to both autoregressive and diffusion. Autoregressive has been studied a lot. Diffusion has not been that much. So we sort of like unify the framework to study both autoregressive and diffusion. But one of the interesting things that comes to mind is the half-life of data. Just like nuclear sciences, half-life basically means at what point can you expect this whatever it is to die within the next however much it was before that, right? So if I had half-life as t, it means that ultimately this particle will die within the next t. Half-life of data means that at what point is this data less than 50% useful for us, meaning that the information that this data could give us, it has given us. And this is the stark difference between autoregressive and diffusion, where after 31 epochs on the 100 million tokens, you are basically done. Half-life has reached. Autoregressive can no longer extract more information from this. But the half-life of the same data in diffusion occurs in 493, meaning that after 493 epochs, you still have 50% more to extract from that data point. So this is something that's interesting. Why is this particularly interesting in multimodality is that exactly we talked about how data is eventually going to run out and we need more scalable algorithms as opposed to being bottlenecked by both data and the algorithm. So now there's also another interesting thing. We talked about the half-life, but what about being almost new data, right? Meaning that at what point in training, like let's say if I have an autoregressive foundation model and a diffusion foundation model, at what point can I expect this the new data points that are happening within the same epoch over and over again to no longer be considered new data points. This happens based off of the tokens. We have drawn this based off of token and the validation loss. So almost after 4 epochs, the data is no longer new for the autoregressive, meaning that the autoregressive has exhausted that data point. It can no longer extract more out of that. It can no longer, you can no longer consider it as something that's going to surprise the model. But for diffusion, that happens after 100, right? So this means that despite the fact that both of these algorithms are working on the same type of data, diffusion treats data points with more, like extracts more information out of these data points. So now there is an interesting moment where we can say, okay, like all of this is great. What should I do? When should I use diffusion over autoregressive, right? The formula is relatively simple. I mean, there's a lot of like evaluations, and, like thousands of experiments that we had to do, and all of these numbers are empirical. But you technically have 2 things. One is the number of tokens, unique data tokens that you have, which is U, and then flops. So you can put in U, solve for flops. You can put in flops, solve for U, figure out at what point roughly diffusion will start beating autoregressive in, in the training that you have based off of the tokens. So this is interesting because a lot of people don't necessarily know what to do if they're in a particular field. They're like, oh, do I choose autoregressive diffusion? If you're, like the message is very clear. If you're compute bottlenecked, go with autoregressive. You're going to be able to get to losses, good losses faster, right? If you're data bottlenecked, go with diffusion because you have more flops. You can go down that line and really optimize your model. And for example, in one of the cases like in robotics, where you have simulations, go with autoregressive, right? If you're doing real-world training, do with diffusion, right? So we hope that this paper will kind of like shed light on making it a little bit more of a selective choice and something that folks are informed about it, as opposed to like, I'm going to try diffusion and autoregressive, both of them, figure out what happens, right? Because that is probably a recipe for disaster. Both of these models are incredibly expensive to train at the end of the day. So this way, at least we can save half of that money. So yeah, thanks for this. So I don't know what happens next,
yes.
Anthony?
I'm here for that. So
okay,
we will now open the floor to any questions.
Oh, questions. Do I have to be as well?
If there are questions about the research.
Okay.
Any questions for the research presentation that we just had?
So from a cost perspective, AR versus diffusion, which one do you recommend? Let's say if money is not a problem or data is not a problem.
Money is not a problem.
Sound is a problem.
Data
is a problem.
I think you can just train a fully connected neural network if you have that
which one
ever.
is expensive to run?
Well,
Go to the microphone, you answer.
oh yeah, sorry. Yeah, so I think that's kind of a very utopian world there, but if I'm looking at the current state of real world, by 2028 we know for a fact that we're going to run out of unique data points, right, where something is going to really shock us, like if we see it again. So my suggestion based off of this is that models that are inspired by diffusion or are under diffusion family have a higher chance, because we know that there's always going to be compute. We can always grab more silicon and just start building these chips. But data, we're running out of the fossil fuel of data, which is internet. So yeah, that's the unfortunate reality today.
The specific year, like what's the rationale behind saying that back to school?
not as fast as, yeah. So the question was, if I understood it correctly, isn't data just increasing on the internet? So wouldn't that make sense to just use autoregressive, I suppose, right? Yes, the answer is both data and compute are increasing, but compute is increasing much faster than data is right now. Especially if you think about it, now that we have LLMs, a lot of generations are going to be based off of the LLMs. So really new data points generated by humans and by professional humans, I suppose, is going to be very limited. Yep, so that's the problem that we face. Any more? Okay.
Why is diffusion better at extracting intelligence from data? Is it just because it can pay attention to more of it at any given training moment, or?
That is a very good question. Here we didn't answer that one. The only thing that we know is that it is not because of better augmentation, meaning that there's definitely things to be studied underneath and figure out, okay, like what is really happening. Because we did experiments on augmenting the data for autoregressive the same way as we did for fusion. It works the same. So. Yep, okay, thanks.
More? Thank you. Do we have any other questions in the audience from the first or the second segment of our presentation on neural operating systems and deployment of AI agents? No? Well, we must have done a good job then. Excellent. Well, thank you for your time.